Hey guys, what's up? Welcome to Unacademy. Let's start our next lesson and we'll be talking about some more important MCQs I have collected from various papers. And if you like my courses, please do like the video and also subscribe to our Unacademy's YouTube channel. And you can also find my entire course list in the description below. So let's see a small introduction about me. This is presented by me, K. Anvesh Samir. You can read more about me over here. If you like my courses, please do rate, review and also recommend my courses by clicking this icon below this video. So let's see the 21st question. A three-phase transformer having zero sequence impedance Z0. Okay, it is a transformer and it has some impedance Z0. It has zero sequence network as represented in the figure. So this is a zero sequence network of the transformer. Okay, the connections of the winding are dash. So I have discussed about these such problems, the zero sequence networks in the lesson, the course I have presented, that is symmetrical components and fault analysis. In that course I have discussed a lot of examples based upon these type of questions. Okay, so to find the answer for the two connections, that is a primary connection, the secondary connection. So obviously the transformer means it will have some primary connection and also secondary connection. So to find the primary connection, the series switch is closed. That means there is a star connected primary with grounded neutral. So the neutral of that star is grounded and the circuit is complete. So the zero sequence, the currents can flow into the circuit, into the transformer from the primary side. So this is the star with grounded neutral. So only one option suits best. So the primary star with grounded neutral, and if you see the secondary, the shunt switch is closed. So closed loops are present in the secondary side of the transformer. So that is possible only in case of delta. So the shunt switch is closed in the sense delta is present on the secondary side. Okay, therefore the answer is option B. So if you want to look into some other examples of zero sequence networks, so this is another example. So the primary of this transformer is delta connected. So I have told you here also the shunt switch is closed in the sense delta. So shunt switch in the primary, it means it is primary is connected in delta, and also in the secondary also shunt switch is connected, therefore secondary is also delta. And another example is we have the primary over here as shunt connected, shunt switch is closed, that means the primary is delta, and in the secondary connection the series switch is not closed but it is open, and also there is no shunt switch closed. Shunt switch is also open, that means delta is not present, star is also not, star with the grounded neutral is also not present. That means only star is present and the neutral is not grounded. So the series switch is open in the sense star connection is present but neutral is not grounded. So if the shunt switch is closed in the sense delta is not present. Okay, if shunt switch is opened in the sense the delta is not present in the secondary. Okay, now let's see another example, delta on the primary side. Okay, we know the shunt switch is closed, therefore delta on the primary side. On the secondary side there is a star connection with grounded neutral. So there is a complete connection to the secondary side. There is a series which is closed in the sense star is present with the ground. Okay, the neutral is grounded. So these are some examples of such sort of problems you can easily encounter in the examinations. So let's see another question. A 100 MVA 100 kV by 33 kV transformer has primary and secondary winding impedances on their own basis in per unit are 0.2 per unit and 0.1 per unit. So what they have actually given is the primary and secondary winding impedances they have given. So what is the per unit basis they have taken is base MVA is 100 MVA and base kV is taken as 100 kV and 33 kV for their 0.2 and 0.1 respectively. That is what he has told right now. Now the effective impedance when referred to the primary side will be dash. So this is what the data he has given, and they are asking us to find the effective impedance when we are referring the total impedance to the primary side. So the per unit impedance is common when it is same whether it is referred to the primary or referred to the secondary. So 0.2 plus 0.1 is nothing but 0.3 per unit. That is the effective impedance when we are referring to the primary side. So that is 0.3 per unit. 0.3 per unit is same even though if we refer to the secondary side also. So 0.3 per unit is constant. Now what they have asked us is the effective impedance referred to the primary side in ohms. So they didn't ask in per unit value, they are asking us in ohms value, ohmic values. Okay, so we have got the per unit value, we have to find the Z actual value. What is per unit value? Z per unit is nothing but Z actual divided by base impedance. Okay, but what is base impedance? Base impedance is nothing but kV square, kV base square divided by kVA base of the per unit, that is nothing but 100 MVA, or you can also say it is a kVA, not even kV, we can also say it as MVA. So kVA or MVA, whatever it is, and kV or V base. Okay, so this is the formula we have derived. I have also derived this expression in the symmetrical components course also. Okay, now we know the Z per unit value. What is the Z per unit value? 0.3. Now we don't know Z actual value, we want to find the Z actual value. What is the Z base? Z base is nothing but V base square divided by kVA base. What is V base square? V base is nothing but 100 kV. So 100 kV is taken as the V base, and kVA base is nothing but 100 MVA. So that is the 100. Okay, now actual value is nothing but 30 ohms. 30 ohms is the right answer, C. Now let's see another question. An alternator has positive and negative sequence reactance 0.2 and 0.2. The ratio between the three-phase fault to the double line fault current is. So they have asked ratio of this fault, three-phase fault current to the line-to-line fault current. So three-phase fault current, in the sense, what is the formula for three-phase fault current? Three-phase fault current is nothing but E by X. So E by X1. Okay. Now we know this line to line fault current is also nothing but root 3 times of EA divided by X1 plus X2. So there is no ground component, therefore there is not X0 also. Even though X0 is given, we don't even have the value of X0 in the data. So line to line fault current is nothing but this formula, and three phase fault current is E by X1. Okay. Now the EA gets cancelled and we have this equation. Now what is X1? 0.2, X2 also 0.2. So 0.4 divided by 0.2 multiplied by divided by again root 3. Okay. So 1 by root 3 times of 0.4 divided by 0.2 is nothing but 2 by root 3, which is nothing but 1.155. That is nothing but option C. It's not D, its option is C. Okay. There is some mistake, error. Okay. Now let's see another question. A shunt fault is characterized by dash. So whenever a shunt fault occurs in the system, what happens is the voltage decreases and the current increases. So whenever the current is increasing, you can say the voltage has dropped in that particular phase, and the reduction in the frequency occurs. So frequency is decreasing in that particular phase, and also the power factor. So these are the three things what shunt fault is characterized by in general. Okay. Now let's see another question. The two alternators of equal internal reactances 0.2 per unit. These two are interconnected through tie bar reactor. So we have two generators, two alternators, and these two are connected through a tie bar reactor. The tie bar reactor reactance value to get the three-phase fault current at the terminal volt of the first alternator as 6 per unit. So this is the alternator of one of the alternator. So what they asked is, what should be the tie bar reactor value, reactance value, to get a three-phase fault current at the terminal of the first alternator. So where is the terminal of the first alternator? This is the terminal. This is the terminal of second alternator. So these are the terminals of these alternators. So a fault has occurred at this terminal, and the fault current should be 6 per unit. So three-phase fault current value is given 6 per unit. So three-phase current is nothing but E by X. So this value should be equals to 6. So what is this E value? E value is nothing but 1 per unit, but we don't know what is this equivalent reactance. So if you want to see the equivalent reactance across this point, so these two are in parallel. So XR plus 0.2 is parallel to the 0.2. Okay. Now this equivalent reactance is nothing but 0.2 into 0.2 plus XR divided by 0.4 plus XR. So this is the equivalent reactance value, and if we substitute this in this equation, we get tie bar reactance value as 0.8 per unit, that is option D. Now let's see another question. The positive, negative and zero sequence reactance of generator are given 0.1, 0.06 and 0.02. Now if the line to ground fault current is given as 20 per unit, so the line to ground fault current is given IF, okay. Now then the three-phase fault current at the terminals of the generator will be dash. So to find this, you just need to know the formula line to ground fault current and three-phase fault current. So line to ground fault current is given as 20 per unit. They have asked for the three-phase fault current value. So what is the three-phase fault current value? It is nothing but ER1 by XR1. So ER1 divided by XR1 is nothing but given, okay, 0.1. That is a positive sequence value, okay, positive sequence reactance. XR1 is given 0.1, but ER1 is not given. To find this ER1, we are going to use the LG fault current value. So what is the fault current of LG? It is nothing but a 3 ER1 divided by X0 plus X1 plus X2. Okay. Now 3 times of ER1 divided by X0 is given, X1 is given, and also X2 is given. Now substituting these values, we get ER1 equals to 1.2 per unit. If we substitute this in this equation, we will get fault current of the three-phase current is 12 per unit. That is option B. Okay, 12 per unit. Now let's see another question. The base kV and base MVA are halved and the per unit impedance new value is 0.5. So they have already given the per unit new value and they are telling the new base kV and the new base MVA are halved of the original values. The per unit impedance of the original circuit element is dash. So they have given the new per unit impedance and they are asking the old per unit impedance. So they have given the base kVA and base MVA values. So the old base kVA is given and they are saying the new base kV is half of the old base kV. Similarly for MVA also, the new base MVA is half of the old base MVA. So that is the main concept they have asked. If you have any good idea regarding this formula, you can solve easily about this question. And remember, they are asking the old per unit value, not the new per unit value. Okay. Now using the values given over here, I have substituted them in this equation, and the answer is 0.25 per unit. Okay. This is the old per unit value. That is option A. Now let's see another question. The positive sequence current of a transmission line is dash. So the positive sequence current is always equal to the transmission is equal to the negative sequence current of the transmission line, because impedances, both the positive sequence impedance and negative sequence impedance are same in a transmission line. Therefore you can say option D is the correct answer. Similarly for the fault at the terminals of a synchronous generator, the fault current is maximum for dash. So whenever a fault has occurs at the synchronous generator, now the line to ground fault has a maximum impact on the synchronous generator. So therefore we can say the fault current is maximum for line to ground fault. So synchronous generator has most severity for a line to ground fault. It is prone to more fault that too for line to ground fault only. That is the only drawback we have in these scenarios. Synchronous generator is prone to more faults in line to ground faults. Okay. Generally, the synchronous generator is very less prone to faults. But if any fault has occurred, then the fault probability will be very high for a line to ground fault. Okay. So these are the questions regarding this today's lesson. I will be talking about some other important questions in the coming lesson. If you like my courses, please do follow me on Unacademy and also rate, review and recommend my courses by clicking this icon below this video. Also, if you have any questions, please do comment below. I will be answering them. Thank you.